Yeah.
There we go. We're live.
Hello.
So anyway, to answer your question, so numbers 7, 8, 9, and 10 are, yes, those are identical to 6 in that you just look at like on 7, okay, like on 7, there's 2 possible spots. There could be a jump, right? On 7, the jump could happen at, we'll get to the true false in 2 seconds. But so someone asked, do you do 7, 8, 9, and 10 the same way you do the ones on number 6? And the answer is yes. So like on 7, just real quick overview of 7, you got to check -2, right? Is there a jump at -2? So where are you plugging the -2 in? Yeah, to the top 2. Where are you plugging the 4 in? The bottom 2. And then there's one last thing you got to consider on this one. At 0, there's an asymptote. And 0 is between -2 and 4, so that asymptote would get included in the function. So that's all you got to do.
Okay.
Number 11. These are the weird ones. True or false? Okay. Did I ever tell you guys about? I'm sure I must have told you about my professor, who would always conduct class like this. Like most of the time, he would just be like, "If f of 2 equals 5, then limit of f of x as x approaches 2 equals 5. True or false?" Maddie. You'd say your name like aggressively and like look at you. You'd be like, true. And you'd be like, Mime, do you agree or disagree?
No.
I neither agree nor disagree. So, okay, 11a. If f of, guys, what does it mean to say f of 2 equals 5?
Then add
Let's back up a little bit. What does it mean?
X is 2, y is 5.
It says
Yes. The first part says if f of 2 equals 5. So that's all we know about the function. Now, is it necessarily true that the limit of this function is going to be equal to 5 as x approaches 2? Certainly not.
Why?
The limit might not even exist. Well, here's one counterexample.
Oh, just because we don't know. Like,
Oh, so
is what
we
you're
don't know
saying.
it. That makes
Yeah.
it.
Right, so okay, let's review some logic first. Okay. This stuff is actually kind of undertaught nowadays, which is a little unfortunate. But so consider this statement. I'm going to make a statement. Okay. If an animal lives in the ocean, I'm just going to abbreviate this. If an animal lives in the ocean, then it's a seahorse. True or false?
I'm just kidding. This one's not. I'm just saying that's a big word that I learned.
That's a good
today.
word. Yeah, that's great.
Thank Miss Vestal.
Yeah, syllogism. Yeah. That would be like saying I think a syllogism, unless I'm mixing up that and modus ponens, would be if I say
It says if a seahorse lives in the ocean, or it's like something like.
I mean something like this. If an animal is a lion, then it's a mammal. Bob is a lion, therefore we know Bob is a mammal.
Yeah,
That kind of thing. This is simpler than that. This is just, is this a true statement or is it a false statement? It is a false statement because, but wait a second, I looked in the ocean earlier and I saw a seahorse. That's very tricky for people. It does not occur easily in most people's minds that, well, this maybe is a little bit easier, but mathematically, these are the same thing. So if for this problem you said, oh, but what about this? What if I drew a nice continuous function like that? Wouldn't it be true?
But we're just basing off the one point, right? So we don't know what's
Right. The question is saying, if f of 2 is 5, does it have to be the case that the limit is equal to 5? No. So like this is saying, if you know an animal lives in the ocean, is it always the case that animal must be a seahorse? No, it is not true. Okay. Because a counterexample would be a sea lion. Or a sponge. Are sponges animals?
Yes.
They are. Sea sponge. So this first one, A is false. How about B?
But how do you counter example it? Oh, you just draw.
This is a counterexample. So why is this a counterexample? Because this counterexample I showed you an example where f of 2 is, in this picture, is f of 2 equal to 5, the way I drew it? Yeah. F of 2 is equal to 5.
But it's not a limit.
But the limit, as x approaches 2, is not 5. So to do a counterexample, it's like the if ocean then seahorse. Sometimes kids will make a mistake on the ocean seahorse thing. They'll say, "Oh no, I'll give you an example. How about a bald eagle?" You're like, "But bald eagles don't live in the ocean, so that's not a good counterexample." Your counterexample has to be in the ocean, but not be a seahorse, right? That makes sense?
The shark in the box.
Damien Hirst. There you go. You can look him up. He's done a lot of really famous stuff.
It's so sick.
I certainly like Damien Hirst a lot more than Jeff Koons.
Even his name sounds bad.
Damien Hirst.
No, Coons.
Okay.
No, like Jeff.
Okay. 11b. If f of 1 is equal to 4, then the graph of the function y equals f of x contains the 0.14. That is true. That's just by definition. That's literally what, when you write this, that means that when x is 1, the y value is 4. So yes, the 0.14 lives in the graph. That's true. 11c. If the limit of your function as x approaches 3 is equal to 1, then the function is continuous at 3.
Wouldn't that be true because it's approaching from both sides?
This is false.
Why?
The question that you ask yourself is, can I draw a function where this holds true? So let's do this. Can we draw a function where this holds true? Oops, sorry. But the function is not continuous.
Oh, because
at
it
3.
has to
it has to-
always.
It has to, so yeah, so you're always playing a game of like, can I come up with a counterexample? Okay? You're like that contrarian person who's always like, well, actually, okay? So here, does the limit exist?
Yeah.
But is the function continuous at 3?
No.
No. So this one, so C was false.
That one's kind of tricky.
They're all tricky. Okay. But the hard part is to get your thought process working in the same way it works. How many you guys all find that ocean and seahorse one easy, right? Because yeah, I don't even know why that is the case really, why it's so much easier. Because logically to prove that statement false, you have to take your mind and start thinking about things that live in the ocean. I guess it's because there's so many things in the ocean that aren't seahorses. Whereas coming up with a counterexample, it's a little bit more specific. You have to draw it in a very special way. Anyway, if f is discontinuous at 3, then the graph has a vertical asymptote at 3.
That's false.
That is
Could be a
false.
whole.
Very good, very good. Counterexample for D would be pick any other discontinuity. How about a jump?
We can literally draw the same thing we just drew from the.
Very good. It could be the exact same graph actually. Yeah. Or how about that? That would also work for D in counterexample. Now, look at E. You're like, wait a second, do I have deja vu? E looks so similar. It says, if the graph has a vertical asymptote at 4, then the function is discontinuous at 4. That one's true. That's called a converse, right? So converse meaning true or false. If you live in the ocean, then you're a seahorse. False. Converse, if you're a seahorse, you live in the ocean. I guess I was thinking true. Then I'm just like, what about one that lives in an aquarium?
Right.
Yeah.
Yeah. So if you want to get technical, if a wild seahorse lives, but you get the idea. Like you can have a statement that a maybe simpler one is, if you're a mammal, then you're a lion. False. If you're a lion, then you're a mammal. That's true. So some statements can only go one way. F says, if f is discontinuous at 3, then 3 is not in the domain of the function.
That's true.
No,
That's
there
false.
could be a jump thing, or like just a random
Oh,
point.
very good. Yeah, a jump would be this would be a good counterexample. Or we could have taken this guy and just added an extra point. And now, do you see how 3 is in the domain of the function, but the function's not continuous? So again, you need a function that is discontinuous, but does have 3 in the domain. G is the big one.
Oh boy.
If f of 4 is 2, so it says if f of 4 is 2, and the limit of the function as you approach 4 is equal to 2, so that means I have to be approaching from both sides. Oh, sorry, I actually read my question backwards. Sorry. It says if it's continuous and f of 4 is 2, does the limit exist?
If it's continuous.
Yeah.
The answer to this one is true. The reason I read it backwards, full disclosure, is this is actually the definition of continuity is if the limit exists, so if you're coming at the same y value from both sides and the actual y value is there, then you're continuous. And that one goes both ways. So if you're continuous, then the point exists and the limit exists, but also the other way. If the limit exists and the point is there, you're continuous.
If the limit exists and the point is filled in where the limit exists, basically.
Yeah, so here, I'll give you one. This is a total giveaway here. 12G, this will be some food for thought for you.
Okay.
12G is true. I guess it's your choice if you want to put some thought into that one. Why is that true? What it's saying is that any x value you pick any x value, call it C. If the function is continuous everywhere, then no matter what number you pick, the limit at that point is going to equal the y value of the function at that point. And that's a really good definition of continuity. So anyway, you know what else? Let's I know the bell's gonna ring, but we're sadly the long period of time. So I'll really quickly go over like the last couple of questions, and then I won't have to record any more videos.
One more?
I won't have to record any more because I'll have covered everything. I guess unless if we have a day where we maybe answer a bunch of questions, maybe I'll record that. But.
That would be nice. So I have a few.
Well, maybe the last minute of class, I can answer your questions here. So 17 says, what's the value of A that makes
You're going to 17.
17? Yeah. So the rest are just true falses. Obviously, we'll have class time to confirm and make sure that we're not confused on those. Don't worry. But the rest are just true false questions. I've already kind of covered the logic of true false. So the last thing is just this. 17 says, what's the value of A that would make this thing continuous everywhere? So who thinks they have an idea? That's what we're looking for. There's some special value.
Everywhere?
Yeah, so it says, what would you have to pick for A? What number would A have to be?
Wouldn't you just plug in 2 into the
It'd be 2
combination to figure out what your y value would be?
That is exactly the case, yes.
Wonderful.
Wait, what do you do?
Maddie just told us the answer. Wouldn't you just say, well, to be continuous, wouldn't this y value from plugging into have to equal this y value from plugging into? Wouldn't this have to equal this when x is 2? Right? So let's do it. Plug 2 in. You get 2 cubed minus 4 times 2 has to equal 1/2 times 2 plus A. So this is 0. This is 1. So it turns out that A would have to be the number -1.
Wait,
Oh, and then draw a rough sketch of the graph. So
Oh boy.
the graph, oh boy. Don't worry, it's not that scary.
Okay.
This guy, well, we already figured out that it's equal to 0 when x is 2, right?
Yeah.
So here's 1, 2, tie my shoe. It's a cubic, right?
So it's gonna be like that on the other side too.
And it's yes, exactly. And it's an odd function. By the way, the nice way to do that is that if you factor out the x, you can see there's 3 x-intercepts, 0, 2, and -2. And so if you graph that,
Wait, how'd you get the -2?
because he.
well, by factoring it.
Oh.
So if I factor this into this, I can see that 2 and -2
You just
both
found
make
all
it
your
0.
x-intercepts.
Yeah, exactly. Or as we pointed out, that basically it's a symmetrical graph.
Okay.
That is an odd function, so it'd be symmetrical. But anyway, and then it turns into a 1/2 x minus 1, but we already established that it's continuous everywhere, so I don't even have to think that hard. I can just draw the linear part.
Okay.
There we go, we're done. Alrighty.